Chapter 1.7, Combinations of Functions and Composite Functions. So in this chapter, we will talk about finding the domain of a function given its equation, combining functions using various algebraic operations, and forming composite functions as well as the properties of those types of functions. So first, we've already talked a little bit about domain when we dealt with relations. We talked about how to find the domain given a graph or a set of numbers, etc. But now we're going to talk about how to find the domain when we have an equation. So to do this, remember that essentially the definition of domain is all values that x is allowed to be. So we start with a domain of all real numbers and then we remove what doesn't work. So the things to watch out for, at least for us right now, there's only 3 things you have to be mindful of. Denominators cannot equal 0, even roots cannot contain negatives, and piecewise given domains. So denominators cannot equal 0. We should already know that. Dividing by 0 is not okay. Even roots cannot contain negatives. We can't take the square root of a negative number, but it's not just square roots, we cannot take the 4th root of a negative or the 6th root of a negative, etc. Any even root causes a restriction to our domain. And then we've talked about piecewise functions in chapter 1.3. So if you don't remember how those work, go back and review that video or those PowerPoints. Because essentially with a piecewise function, sometimes there will be restrictions based on the pieces of the function. It might just stop at a certain point. And then sometimes you'll just be told a domain. Essentially, along with piecewise, sometimes you're just told a domain and that's it. So sometimes we restrict our domain not based on the algebra of the function, but based on just being told some information or based on some word problem specifics like reality, like we cannot have a negative distance, etc. But generally, when we deal with equations, the main things we want to look at are we're looking for denominators and we're looking for even roots. So first, denominators cannot equal 0. So in order to find the domain of a function that has a denominator in it, we just take the denominator and set it equal to 0 and figure out what causes a problem. What causes that denominator to be 0? So I'll take in this equation f of x equal to x plus 1 over 2 minus x. 2 minus x cannot be 0. So what would cause that? We just solve that algebraically. We subtract 2 from both sides, etc. And we're going to get x cannot be 2. But remember that we usually want to write our domains in interval notation in this class. So to remove 2 from the domain from that all real numbers, to remove the number 2, we're going to have to unify 2 sections of our number line. Because essentially what's going on is we have this number line, and then we have the number 2, and we're including everything this way and everything this way, but not the number 2. So we have to cut that out of our domain. So this side, the left side, is negative infinity up to 2, but not including 2. And then the right side is 2 up to infinity, but not including 2. And so together, we unite those 2 pieces. So make sure if you're removing a part of your denominator, you don't just say, oh, it's 2 to infinity now, because you can still have negative numbers, that's fine. You just have to cut out that one number. There's only one number we're removing here, not an entire interval. Now, for even roots cannot contain negatives, what we're going to do is we're going to take anything that's inside of our even root, the entire thing under that root, and we write it as, in this case, 7 minus x has to be greater than or equal to 0. That's going to be our domain. And then we solve for x. So I subtract 7 from both sides, I multiply by negative 1, which is going to switch the symbol to a less than. So we're going to end up with x is less than or equal to 7. So again, negative x greater than or equal to negative 7, x less than or equal to positive 7. Because remember, when we multiply or divide by a negative, it switches the direction of our inequality. So x is less than or equal to 7. So in other words, our interval notation says from negative infinity to 7, including 7. Notice the inclusion, the or equal to, because we can take the square root of 0. We can't take the square root of negative 1, but we can take the square root of 0. That's fine. The square root of 0 is 0. So we include our endpoint here. Now, what if those two things, that even root and that denominator, were combined? What if I had f of x equals x plus 1 over 2 minus x times the, in this case, fourth root of 7 minus x? The fact that it's a fourth root doesn't actually change what we do. So even though it's a fourth root instead of a square root, we still have this problem of the inside of that root has to be positive. So we would have two problems here, that that 2 minus x cannot be 0, and 7 minus x has to be positive, but this time it also can't be 0. So in this case, we're going to get two situations. X cannot equal 2, and x is less than 7. So when we write that as a combined interval, well, let's look at the number line again. So here is 2, and we're cutting out 2. And then 7, we're also cutting out 7, but we're less than 7. So we're less than 7, but we're cutting out 2. So that means we are this interval and this interval, which is 2 to 7 and negative infinity to 2. So together we have negative infinity to 2, not including 2, united with 2 to 7, not including 2 or 7. So sometimes you will run into these situations where there's more than one thing going on, where there are square roots in your denominator, where your denominator has multiple things being multiplied together. The point is you just need to make sure that you're cutting out every instance of division by 0 or square roots of positive numbers. Or square roots of negative numbers. So let's look at our common functions and see if we can say what our domain is. We've already talked about how to find the domain from a graph, so it should be pretty simple to do this, but let's investigate a little bit specific about the domains of these functions. So first, for the constant function, our domain is all real numbers. We can see that in the graph very easily, and we know that the constant function is f of x equals c. There's no division, there's no square roots. All real numbers. Next, the linear function, the identity function, f of x equals x. No square roots, or no even roots, no division. All real numbers. Next, f of x equals absolute value of x. So this is, again, this. I've talked before about how the absolute value can be defined as a piecewise function, so we have to be aware of that. But in its piecewise form, it doesn't have any domain restrictions. So in this case, there's no restrictions, domain is all real numbers. Next, we have the x squared. Again, domain, all real numbers. There's no division, no even roots. X cubed, no division, no even roots. Here's where we start having problems, is the reciprocal function, 1 over x. There is division. So the domain, as soon as we have that division, we have to cut out 0. Our domain becomes from negative infinity to 0, and then 0 to infinity, where we do not include 0. So we're just cutting out that 0, but there is a union in our domain. And our range also happens to be the same. Then our 1 over x squared, our reciprocal squared function. Again, we're cutting out 0, because even though x is squared, 0 squared is still 0, so 1 over 0 we can't have. So we cut out 0, it's the same domain, but our range has changed a little here. Then here we have square root of x. For the square root of x, we have a domain from 0 to infinity, including 0. That's what I was talking about when I said we're allowed to have the square root of 0. That's fine. So our base square root of x function has a domain that includes 0. And then our cube root function right here That's all real numbers again, because a cube root is not an even root. It is an odd root, because 3 is odd. So our domain is all real numbers. So now we're going to move on to combining functions using algebra. And this domain stuff is going to come back in once we talk about this combining of functions. So we can do normal algebraic operations on functions by calculating their outputs separately, then performing the operation. Or we can also just write out the operation. So for example, f plus g of x is f of x plus g of x. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And f over g of x is f of x over g of x. This is just a notational thing. So let's look at what exactly that means and what that looks like. So f plus g of x, if we have these functions, f of x is x minus 1, g of x is x squared minus 1, then f plus g of x just means we take f of x, we add it to g of x, like so. And then we can simplify. So x minus 1 plus x squared minus 1, that's going to be x squared plus x, and then there's minus 1, combine our like terms, minus 2. F minus g of x is just we're taking all of f of x, x minus 1, and subtracting all of g of x. So make sure when you do that you actually subtract all of g of x. So we are distributing that negative symbol. So this negative gets applied to both the x squared and the negative 1 to give us x minus 1 minus x squared plus 1. So that's why this is negative x squared and there is no 1 left over because it cancels out. Next we have f times g of x, or just written as fg of x often, but sometimes I will often write it with a dot between them as multiplication. There's many ways you can write this, but just f times g of x is f of x times g of x. So I'm going to take all of f of x and multiply it by all of g of x, like so. Remember, when you do this, you have to FOIL. So hopefully you remember your foiling properties. So we get x times x squared is x cubed. Then x times negative 1 is negative x. Then negative 1 times x squared is negative x squared. And negative 1 times negative 1 is positive 1. And so altogether, we get the given function. Finally, f over g of x is f of x divided by g of x, or f of x over g of x. So we just take all of f of x, divide it by g of x. Now in this case, I have shown how we can simplify this function. This is not always going to be the case. In fact, it is rarely going to be the case. But in this case, we can simplify it. So I factored x squared minus 1 and then canceled. But I made a note of the domain of the original before doing that cancellation. So this is just sort of a quick look at something we're going to explore a lot further in Chapter 2 when we deal with rational functions, doing that simplification and what exactly that means. But just make a note that when we talk about domain, we want to talk about it for the original function right here, not the simplified form. All right, so speaking of domain, we can find the domain of these functions by finding the domain of their individual pieces. So in this case, there's no division and no square roots in 3 out of the 4 of these cases. There's no division and no square roots in the original f or g. So the domains were all real numbers for f plus g, f minus g, and f times g. But in f over g, we do have a restriction to the domain. We're not allowed to divide by 0, so whenever x is 1 or negative 1, we would have had division by 0. So you do have to be aware of a change in the domain when you're doing division. The final type of operation that we will be defining is called composition. So when the output of one function is used as the input of another function, we call the operation a composition of functions. This action defines a composite function. So we will use the circle symbol as the symbol for composition. So remember that when I was talking about fg of x, I said that I will often write a dot between f and g to denote f multiplied by g. Dot is different than circle. So if you ever see f circle g like this open circle like this, it means f composed with g at x. That is composition. So circle, not the same as multiplication. Even though we sometimes use a dot as a multiplication symbol, a dot is not the same as a circle. And for some of you that may seem obvious, but I promise there are going to be people who make that mistake. So please, please try not to. Recognize that the circle is a composition symbol, and only composition. So, what is composition? Well, it is defined as f of g of x. We are inputting g of x into f. So, g of x is the input of f, but x is the input of g. So, we can say, so we have to note a couple things. As I said before, f of g of x is not the same thing as f times g of x. Composition is not multiplication. They should not be the same. In fact, they basically never are. So, also note that f of g of x and g of f of x, so in other words, we sometimes say fog and goth, because that's what they look like, f of g and g of f, are usually different. There are cases where they are the same, and those are special, and we're going to talk about those in the next chapter. But in general, they're usually different. So don't get those confused. This is not a commutative operation. Finally, to talk about the domain of f of g, things get a little more complicated. So you notice that in the previous examples, f plus g, f minus g, etc., the domain doesn't change much. Even if, those situations, it was mostly all real numbers, but that's still going to be the case for a lot of situations, is the domain is just going to be a combination of the domains of the previous functions. Whereas f of g gets a little more complicated because the domain is all x such that x is in the domain of g and g of x is in the domain of f. Which is a lot to say out loud, but when you see examples of it and look at it algebraically, it might make a little more sense. So let's actually address an equation. So first, we're going to work with f of g of x, and then we're going to deal with g of f of x to show that these are not necessarily the same. So first, f of g of x, or fog, is composing g into f. Okay, so that means x is replaced with g of x. So in other words, we get 2 times g of x plus 1, which, if you remember our transformations, you should know what that looks like. It would be taking g of x and then doing a vertical stretch and then a vertical shift of 1 and all of that. So you might be able to graph this even easier now. Transformations are all about composition. So now, replacing g of x in, we know g of x is 3 minus x. So I'm now going to write that as 3 minus x. And then I'll simplify by multiplying 2 times 3 minus x, etc., and then simplify it together to get 7 minus 2x as our final answer. So f of g of x is 7 minus 2x. But g of f of x, or goth, is going to be different. I'm placing f into g, so we get 3 minus f of x. Or in other words, 3 minus 2x plus 1. Remember, once again, distribute that negative, so that's 3 minus 2x minus 1, which is then simplified, combined like terms to be 2 minus 2x. Notice that they're not the same because the operation is not commutative. Remember, commutative just means that it works in both directions and you get the same answer. Addition is commutative, but subtraction is not. Multiplication is commutative, division is not. Composition is not commutative. Now let's look at a type of word problem that we could run into that involves composition. So the function c of s gives the number of calories burned completing s sit-ups, and s of t gives the number of sit-ups a person can complete in t minutes. Interpret c of s of 3. So first, s of 3, so the innermost part of this statement, is the inside of the composite. So since the input to s is t, we would then say, well, then t must have been 3, right, from this s of t. So t is 3, and remember that t is t minutes, so we're at 3 minutes. So in other words, c of s of 3 is what's occurring at 3 minutes. Well, s of 3, we know s of t gives the number of sit-ups a person can complete in t minutes. So in other words, s of 3 would be the number of sit-ups completed in 3 minutes. Okay? Then we're inputting s of 3 into c of s. So this gives us the number of calories burned completing s sit-ups. So in other words, it gives us the number of calories burned during the number of sit-ups that can be completed in 3 minutes. So we're putting all of that information together. Specifically, that number of calories burned in 3 minutes while doing sit-ups. So it's all together, and so that's how composition can come out in these word problems, is we're getting excess information. I sort of mentioned this before when we talked about, in chapter 1.2, when we talked about the months versus days, and then I started using the months as numbers instead of as their word equivalent. I said, oh, this is like I have now transformed the months into a number, and then I plugged the number into the function. So that was a composition. Essentially, all I did was I applied one rule and then I applied a second rule after it. That's what composition does, is one rule and then the next rule and then maybe the next rule and so on. You can keep composing. So if we are trying to evaluate a composite function and we're given a table, we just need to look at, we're going to need to know some information about both functions, f and g. So f of g of 3. First, we're going to start out with, we know x is 3, and we are plugging g of 3 into f. So g of 3 is 2, which means that we're really looking for f of 2. Then, f of 2 we know to be 8. So in other words, f of g of 3 is 8. Then, if we're looking at g of f of 3, again, x is 3, because that's the innermost thing. F of 3 is still 3. So, g of f of 3 is the same thing as g of 3. Then, g of 3, we look at our table, and we know it's 2. So, g of f of 3 is 2. So this should maybe look a little familiar from when we looked at the tables of transformations of functions from the previous chapter. Transformations, as I said before, all about composition. That's what transformations are. So this is very related. Now, what about if we're looking at a graph, though? So if I want to use the graph to evaluate f of g of 1, and here I have graphs of both f and g, first I'm going to start by looking for x equals 1 on my innermost function. Here, that would be g. So I'm looking for x equals 1 on the graph of g. And then I follow it up and see what was g. Well, g is 3 when x is 1. So g of 1 is 3. Then I look at, well, then what is f of 3? F of 3 is 6 from the graph. And so my final answer would thus be 6. So f of g of 1 is 6. So we have to go through both graphs in order to get to our final answer. Now, what about if we are evaluating them algebraically? Well, here, use the formula to evaluate f of h of 1. Here we have h of x equals 3x plus 2, and f of t equals t squared minus t. So it doesn't always have to be x for both of them. We can use different letters. It doesn't matter because remember, you can change your letters pretty easily. So if we have this situation, then remember, we know how to write f of h of x. If I wanted to write f of h of x, I would plug in h of x for t. So that would be 3x plus 2 squared minus 3x plus 2. I've replaced both of my t's with h of x. But I don't need to do that in order to evaluate f of h of 1. I can do that and then I can simplify it and I'll have a nice function and all of that, but I can save myself some time because that's not what's being asked. What's being asked is what is f of h of 1. So first, all I have to do is plug in 1 for x. So h of 1 is 3 times 1 plus 2, which is 5. So h of 1 is 5. Then f of h of 1 would be f of 5. So I figure out what is f of 5. I plug in 5 into f, so that's 5 squared minus 5, which is 25 minus 5, which is 20. So in conclusion, my answer would thus be 20. So f of h of 1 is 20, and I didn't need to go through the effort of figuring out what f of h of x was. So last, we're going to look at the domain of those composite functions. I already sort of expressed a very wordy way of saying how the domain works. Here we're going to actually explore it, and hopefully it'll make a little more sense. It's still a bit tricky, but the domain of a composite function, f of g of x, is the set of those inputs x in the domain of g for which g of x is in the domain of f. Okay, so again, it's very wordy. Let's look at what that actually means though. So the steps to finding the domain of f of g. First, find the domain of g. Second, find the domain of f. Third, find those inputs in the domain of g, so we're looking at the domain of g, where g of x is in the domain of f. So that is, we're going to exclude anything from the domain of g that would, where its output is not in the domain of f. Again, still confusing, I realize, but let's apply this. So if I want to find the domain of f of g of x, when f of x is 5 over x minus 1, and g of x is 4 over 3x minus 2, what can I do? Well, the domain of g, I know, is going to be anything that causes 3x minus 2 to be 0. So I'm taking 3x minus 2, the denominator, it's not allowed to be 0. So when is it 0? It's 0 when x is 2/3. So the domain of g is x is not allowed to be 2/3. So in other words, in interval notation, that would be negative infinity to 2/3 unioned with 2/3 to infinity. So all of that is what is allowed in g. Next, we're going to find the domain of f. Okay. Works the same way. X minus 1 is not allowed to be 0, because again, we're just looking at the denominator here, so x cannot be 1. So here are our two domains. And if we were dealing with any of those other operations we worked with before, if this was f plus g, then the domain would just be everything except 2/3 and 1. If it was f minus g, same thing, everything except 2/3 and 1. F times g, same thing. F divided by g, same thing, but possibly dealing with an extra instance of division by 0 you have to check. But in this case, it doesn't work that way. We're actually not going to cut out x equals 1 from our domain. Instead, we're going to cut out g of x equal to 1. So that's the question, is when is g of x equal to 1? So we solve that. 4 divided by 3x minus 2 equals 1. We're going to do cross multiplication. So remember, to solve this, we cross multiply. So it'll be 4 equals 3x minus 2. And then we add 2 and divide by 3. So add 2, divide by 3, to get x equals see. Oh, to get x equals 2. So that'll be adding 2 is 6, divided by 3 is 2. Yeah, so x equals 2. So note that our new domain is actually going to be what caused division by 0 in G, and then the output g of x causing division by 0 in f, which is a little weird. But our end domain of f of g is x cannot be 2/3 and x cannot be 2, which is given in interval notation. It's a little obnoxious, but that's how we would write it in interval notation. But note, x equals 1 is actually in the final domain of f of g. If I plugged in x equals 1, we can see f of g of 1, well, g of 1 is 4 over 3 minus 2, which is 4 over 1, which is 4. So f of 4 is 5/3. That's fine. That's why 1 is in the domain, because plugging in 1 into f of g doesn't cause division by 0. But if I plugged in 2, it would cause division by 0, because that would give me f of g of 2 equals f of, so 4 over 6 minus 2 is, so 4 over 6 minus 2, which is 4 over 4, which is 1, f of 1, which we know to be undefined, because that is division by 0. So that's how you find the domain of the composite function when you're not just writing out the function itself. So the domain of the composite is find the domain of g, find the domain of f, and then find what causes g to be that problem and remove it. And then the last thing, now that we have everything about composite functions, is just doing the opposite, decompositing or decomposing functions. So we can look at a composite function and decompose it into 2 or more separate functions. There may be more than one way to do this, so we can choose whatever is best for the situation. So for example, f of x equal to the square root of 5 minus x squared can be decomposed as f of x equals g of h of x, where g of x is square root of x and h of x is 5 minus x squared. So remember, that would look like g of h of x is, we start with g of h of x, but h of x is 5 minus x squared, so that's square root of 5 minus x squared. So yes, it does look like f of x. But we also could have broken it down into g of x is square root of 5 minus x and h of x is x squared. Because then g of h of x would be square root of 5 minus h of x, which, replacing h of x with x squared, is square root of 5 minus x squared. So we're right back to what f was. So there's more than one answer, and there may be even more than this sometimes. Sometimes there's only one, like, obvious answer, so it's up to you to say which one comes to mind if you're asked a question like this, because there isn't always a unique answer, and you might not be wrong just because you have a different answer than your neighbor. So that's it for this chapter. Another long one, I know, but we're getting through this unit. We're almost done, just 2 more to go. Once again, make sure you're practicing. Look into the domain questions especially, because that will definitely come up throughout our throughout the chapters we go through. So make sure you understand domain now so you're not thrown off by it later, because it will keep coming back.